So this is the second video dealing with reaction mechanisms. In this short video I'll talk about rate determining step and define that for you, although I think that's fairly self-explanatory, that term. And then we'll go through an example of a reaction mechanism, and you'll see some of the information you can get from a mechanism, some of the things you need to be able to communicate from a mechanism. And finally we'll look at a reaction mechanism in terms of potential energy diagrams. So why don't we get started on that right now. Start with an analogy. So those of you who have been to New Zealand may be familiar with this sort of scene. Basically, if you fly into New Zealand, as I did quite a few years ago, you land at Auckland Airport, you hop in a car, rental or whatever, and you start driving. And so you get out of the airport on sort of a 4-lane road, and the speed limit's probably 80. I can't recall exactly, but the speed limit will be 80, so you're moving along reasonably well. You then get onto a larger sort of 6-lane highway heading out of Auckland, and there the posted speed limit's 100 kilometers an hour, and you're booting along pretty well. Then you get into some country roads. They can be mostly 2-lane roads, and the speed limit's probably 80. You might be going a little quicker, but again, you're moving along reasonably well. You get into windy country roads, speed limit maybe posted as 80. You're probably not going that fast because they're kind of windy. And eventually, you hit a flock of sheep. And if you are driving in New Zealand, you will hit a flock of sheep. So the reason I think this is a useful analogy is that reactions kind of occur in the same fashion. You have a series of steps, this mechanism, and each one of those steps proceeds at a certain rate. And all of those rates are going to be different. But the entire mechanism cannot proceed any faster than the slowest step. That is the flock of sheep getting away. And so with a reaction mechanism, you only proceed as fast as the slowest step. Just like in New Zealand, you only proceed as fast to your final destination as the flock of sheep you encounter allows you. So you can sort of think of that analogy as useful in viewing a mechanism. We're going to have a series of steps, one of which will be the slowest step, one of which will be the rate determining step. So, defined, the rate determining step is the slowest step in a reaction mechanism, that one reaction that will determine the overall rate and hence the rate law for the mechanism. And so rate determining steps are very important in mechanisms because the rate is directly related, the rate of the overall equation is directly related to the rate of the rate determining step. Now, just a few things to remind you of. Reaction mechanisms are just a theory, so chemists spend quite a bit of time doing experiments, initial rate law stuff that we've already looked at, to determine the rate law. But they also use supposition. They also put together different elementary processes that might lead to a working mechanism. And so each step must be elementary in the reaction mechanism, involving no more than 3 reactant molecules, usually in 2. 1 and 2 are certainly more likely than 3 in terms of molecularity. The slowest rate determining step has to be consistent with the experimentally derived rate law. So a rate law is determined experimentally. In your mechanism, you must have an elementary process that gives you that exact rate law. And we saw before that an elementary step actually allows you to write a rate law. So you just have to have an elementary step in there that is consistent with your experimentally determined rate law. Finally, the elementary processes have to add up to the overall equation. And that becomes important as well because there's no point in writing a reaction, balancing it, and thinking that's the actual reaction without being able to generate that reaction from all of your elementary processes. So we're going to see how that works. So this is a pretty commonly studied, or was commonly studied, reaction in terms of trying to come up with a plausible reaction mechanism. So here we have hydrogen bromide plus oxygen yielding water and bromine, all in the gaseous state. That's why it was a useful reaction to be able to study. Gases are pretty easy to manipulate. So the reaction as written is unlikely to occur, and why would that be? Well, look at the molecularity, 4 and 1 in terms of stoichiometry. So what we're looking at here is you'd require a 5-particle collision. And we saw from the previous video with our billiard ball table that a 5-particle collision with particles at or above activation age and orientation. So the plausibility of that is highly implausible. That's probably not going to happen. So that reaction, hydrogen bromide, 4 molecules colliding with 1 molecule of oxygen, is probably not going to happen. But we can still write a predicted rate law. And again, as I mentioned last week, a predicted rate law just simply comes from the stoichiometry. So we would predict this. So hydrogen bromide raised to the power 4, oxygen raised to the power 1. So again, a predicted rate law would be as such. The problem there is, again, 4th order with respect to HBr, and 5th order overall. So those two numbers just don't really allow for that to be the likely way that this reaction occurs. So those high reaction orders mean it's probably not going to happen as written, even though we would predict it. So we got to go to the experiments. And so here's some experimental evidence. Increasing oxygen increases the rate, so the reaction is 1st order in O2. Increasing hydrogen bromide does increase rate, but not based on the stoichiometry, so it's not going to be raised to the power 4, but it does increase rate. And overall, it's a 2nd order reaction. And so we can write an experimentally derived rate rate. We have enough information. 1st order with respect to O2. So there it is. And it's 2nd order overall, which means there must be HBr, and it must be to the 1. And so there we go. There's 2nd order overall, 1st order in oxygen, 1st order in HBr. So that's the experimentally determined rate law. So now what we need is a mechanism that gives us that rate law and the overall equation, which, as you see at the top there, 4HBr plus O2. So this is a proposed mechanism. And so you look at the different steps. First of all, if you remember the guidelines that we use for a mechanism. So step 1, that's a bimolecular process. 1 molecule of HBr, 1 molecule of oxygen, bimolecular. Also notice it says that this is the slow step. So that's obviously very important. Step 2, step 3, step 4, all bimolecular processes. So we need to be able to identify the rate determining step. We already did that. There's the rate determining step. So again, a part of the mechanism that is identified to be the slowest, or proposed to be the slowest possible step, and we'll get a sense of why that's the proposed in a minute. So we've identified the rate determining step as slow. There it is. That's step 1. From this mechanism, we also need to be able to come up with an overall reaction, identify reaction intermediates, and come up with a rate law. Okay, so let's carry on with that. So first of all, come up with an overall reaction. Well, what you need to do is look at the different steps and look at what's produced and what is reacted. So in step 1, we have HBr combining with oxygen. We produce this complex, this HOOBr. So that's the product. So there, it's a product. Well, if you look at what happens in the next step, there's my HOOBr, but now it's a reactant. So this product immediately becomes a reactant, and it gets used up. If you notice, there's no HOOBr left. We have new products. Well, look at this product, HOBr. HOBr as a reactant. Product becomes a reactant. Becomes a reactant. So those molecules that I've just identified are not part of the overall equation. HOOBr gets used up. There is no HOOBr left. HOBr gets used up. There is none left. So what do we have left? Well, here we can identify what we have. So in our first step, we have these two reactants. Step 2, we have that reactant. Step 3, we have that reactant and these products. That reactant and these products in step 4. So there's everything that's left, and so we just put all that together and we get our overall equation. So HBr, but we actually have 1, 2, 3, 4 moles of HBr. So HBr plus 1 mole of O2, there it is, yields 2 moles of water and 2 moles of Br2. So there is our overall reaction. We've generated it from our proposed mechanism. So the mechanism has to be able to give you the overall reaction. Well, again, let's just follow that a little further. Identify the reaction intermediates. And so there I've kept them highlighted. So these are the reaction intermediates. So the reaction intermediates, as I mentioned, chemical species that are produced early in a step in a mechanism and then consumed later on. So they never appear in the overall reaction. So that allowed us to get rid of these intermediates and be left with what would appear in the overall reaction. So reaction intermediates will be seen in the mechanism but will not be seen in the overall equation. Now, proposed mechanism has to be able to give us a rate law. So the rate law, again, stems from the rate of reaction of the slowest step. And since this is an elementary process, HBr plus O2 yielding HOOBr, that's an elementary process, we can write a rate law directly. So R equals K HBr times concentration of O2. So that's the actual rate law. And if you recall from previously, this is the same as our same as the experimentally derived rate law. Which we looked at earlier from our information given about the reaction. So that's important as well. But for you at this stage, all you need to realize is you can write a rate law from an elementary process. That elementary process is identified as slowest is the rate determining step, and that rate law for the rate determining step, and therefore the overall equation, therefore the mechanism, will be that predicted rate law. The rate law you can write directly based on stoichiometry. So that's the rate law. Now, we want to be able to look at this in terms of potential energy diagrams. So again, one of the ideas here with this particular mechanism is that that first elementary step, that HBr plus O2, has a high activation energy. So this is the reaction that's proposed to be slowest, that one step. So any steps subsequent to that cannot go faster until you generate enough of this HOOBr. So there's again the slowest step. Well, let's see what this looks like in terms of potential energy diagrams. And so here we have potential energy diagram, potential energy versus reaction progress, and this is what it kind of looks like. And so we'll explain these humps. Well, let's first of all look at what we got here. So again, there's our reactants in our first step, that first mechanism. And as I said, relatively high activation energy. So there's the activation energy for that first step. So EA for HBr plus O2 is high, but if EA is matched, we get our first product. And so there's our first product, that reaction intermediate, HOOBr. Remember, that's a reaction intermediate. And so the actual reaction proceeds via a relatively high activation energy, but if you get to activation energy, you generate your product. This intermediate can then react, and if it does react, what happens? Well, it has to overcome a second activation energy, but notice there, that's a pretty small EA. EA2 is quite a bit less than EA1. So the implication there is that as soon as you start producing HOOBr, it will immediately react because it has a much lower activation energy. And so you start generating future products. And again, in this case, HOBr. That's a reaction intermediate. And again, another activation energy, fairly low until you get your H2O plus Br2. So there's what a reaction mechanism looks like in terms of a potential energy diagram. These humps then are activated complexes for each of the steps in the mechanism, and at each valley in a potential energy diagram there you get a reaction intermediate within the series of hills and valleys. And so overall, though, HBr plus O2 yielding H2O plus Br2, but via a series of steps, all with different activation energies and different rates. First one, setting the rate. And so that basically concludes how you can look at reaction mechanisms, either as a series of steps or as a potential energy diagram. So I guess that concludes this video.